The time layering of recurrent networks makes them inherently deep networks. A recurrent network is as deep as the length of the sequence on which it is applied. This tends to make a recurrent network very sensitive to the problem of vanishing and exploding gradients. In this video, we discuss two architectures which are specially designed to stable the gradient flows in a recurrent neural network. These variations of the recurrent neural network, they are referred to as long short-term memory, short LSTM, and gated recurrent unit, which is referred to in short as GRU. In order to motivate the LSTM and the GRU, we will revisit the vanishing and exploding gradient problems. We already discussed these problems in earlier lectures, but here we will revisit them in the context of the recurrent neural networks. We will also discuss why these problems are more likely to occur in the case of a recurrent neural network. Now consider a very simple neural network which is very deep, but you have only one node per layer. This type of neural network is illustrated in the diagram on the slide. Now in this case, when you backpropagate the derivative, what happens is that the backpropagated derivative in each propagation gets multiplied by a weight as well as the derivative of the activation at that node. Now unless the product of these two values is exactly 1, the partial derivatives will either continuously increase or they will continuously decrease. Typically, it is very hard to have a situation where these two values are always 1. Furthermore, another issue that creates greater problems in the case of the recurrent neural network is that the weights are shared across different layers. So at least one component of the propagated derivative will be a single weight which is being multiplied by itself again and again. Of course, the derivative of the activation function may be different from layer to layer, but nevertheless the multiplication of a shared weight with itself tends to exacerbate the vanishing and exploding gradient problems. For example, imagine a situation where the weight is always less than 1. In that case, if the activation derivative is also less than 1, which does happen to the case with most nonlinear activations, your derivative, your backpropagated derivative will always vanish. On the other hand, if the shared weight is too large, then the backpropagated derivative will always increase. LSTMs and GRUs are ways of addressing this problem. Now, in the previous slide, I showed you an example in which each layer of the network contains only one node. You can generalize this argument to a network in which each layer contains multiple nodes. Now, imagine you have a situation where the gradient in the tth layer is denoted by GT. In that case, we already discussed in an earlier lecture that the backpropagated vector of gradients is given by the transpose of the Jacobian multiplied by GT plus 1. Now, in this case, you are repeatedly multiplying with a matrix rather than multiplying with a scalar. Now, the way this Jacobian is defined is that the ijth entry of the Jacobian is simply the ijth entry of the square hidden to hidden matrix WHH, which is multiplied with the derivative of the tan f function at the current value in node J. So when the gradients cause successive multiplication with the transpose Jacobian, which is referred to as P delta P inverse, then multiplying by m times, you can show that the transpose Jacobian to the power of m is given by P delta to the power m P inverse. Now this delta to the power m, this is a diagonal matrix being multiplied by itself m times. And when you multiply a diagonal matrix with itself m times, each entry in the diagonal gets multiplied by itself m times. So in this case, the largest eigenvalue decides everything. So if the largest eigenvalue is larger than 1, then the diagonal matrix, its largest eigenvalue keeps increasing. So the overall matrix, the transpose of Jacobian to the power of m also blows up. On the other hand, if the diagonal matrix is less than 1, then this matrix to the power of m, it vanishes, and the transpose of the Jacobian to the power of m also vanishes. So in both cases, you can see the vector-wise gradient propagation, the vector of gradients, that's gt, either explodes in magnitude or it vanishes in magnitude. Now, there are other issues with recurrent networks which are related to the fact that it is hard to retain the information in a hidden state with successive matrix multiplications. Now note that matrix multiplication is a very strong operation which is inherently short term. It inherently changes the magnitudes of the gradients when you are propagating back from layer to layer. And there is no mechanism for fine-grained control of what information to retain from hidden states. The notion of LSTM introduces the idea that you can copy a part of the state from one layer to another. Copying a part of the state from one layer to another is a gentle operation. So when you copy, the gradient flows are greatly stabilized. And the way this copying is controlled is with the use of gates. So the gates decide whether or not to copy or how much to increment a specific state. In the particular case of the LSTM, because we are working with continuously differentiable operations, we use analog gates, that is gates with continuous values between 0 and 1, rather than discrete binary gates with values of either 0 or 1. So, in order to introduce the LSTM, let us revisit multilayer recurrent networks, because we are going to introduce the multilayer LSTM for greater generality. So, it is good to refamiliarize with the notations that we discussed in an earlier lecture. So, in this case, you can see that the hidden state, which is denoted by HTK. Now, note that the superscript denotes the layer number. So, in this case, you have 3 layers to your multilayer recurrent network. So K will vary between 1 and 3. And T, of course, is a timestamp. It can take as many values as a number of time layers, which in turn depends on the input length. So HTK is defined by this matrix WK multiplied by HTK minus 1, HT minus 1K. Now you apply the tan F function to this in order to get HTK. Now this matrix WK is a P cross 2P matrix. So when you multiply a P cross 2P matrix with a 2P dimensional vector, so this 2P dimensional vector on the right hand side, it's essentially the hidden state in the previous timestamp stacked up with the hidden state in the current timestamp but in the previous layer. Now one point that you need to note is that the value of k is equal to 1 needs to be treated specially, because when you have k is equal to 1 on the left hand side, then on the right hand side there will be a term where k minus 1 becomes 0. So that ht0 is essentially the same as xt, which is the input at time t. That's because of when you're looking at the first hidden layer, then this recurrence equation, instead of using htk minus 1, it will use xt. So we always need to treat the case of k is equal to 1 a little bit specially, and that special treatment is also carried over to the LSTM and to the GRU. Now let's discuss the issue of long-term versus short-term memory. A recurrent neural network only carries forward a hidden state HTK across time layers. Now, as we discussed in the previous slide, this hidden state is inherently short term because it tends to get scrambled by matrix multiplications. The LSTM carries forward both a hidden state and a cell state. So the hidden state is denoted by HTK, which is the subscript corresponds to the time layer and the superscript corresponds to the multi-layer. That's the layer between the input and the output. And typically this value of k will be a small number between, let's say, 1 and 3. So because typically you don't tend to use too many layers in one direction. And similarly, you have a cell state. So for each hidden state HTK, you have a cell state CTK. So the hidden state is like a short-term memory which is updated more aggressively, where the cell state is like a long-term memory which is updated gently. As you'll see, there is some level of copying occurring, and the level of copying is controlled by analog gates. And the other thing that you do is that because the cell states are very stable, because you're allowing partial copying from layer to layer, you allow leaking between the short-term and long-term memory. So you allow some of the long-term memory to be leaked into the short-term memory, and that kind of leaking also stabilizes the gradient flows of the short-term memory. It also stabilizes the hidden states. So let's go into the details which will explain what I mean by what I just said. So let's assume that the hidden state, that's your HTK, and your cell state, that's CTK, they are both p-dimensional vectors. In this case, the matrix, so again, in your multilayer neural network, you had this matrix WK in order to transform from layer to layer. Here, your matrix WK, you have a similar matrix WK, except its size is much larger. So here, its size is 4p cross 2p. So when you have a matrix 4p cross 2p and you multiply it, now this, if you look at equation 2 on the right hand side, the rightmost expression, it's a vector of size 2p. So you're multiplying a vector of size 2p with a matrix of size 4p cross 2p, which is going to create a 4p dimensional vector. This 4p dimensional vector, instead of treating it like a hidden state, these are actually the gates that you create. 3 of them, so 3p, so you divide into 4 parts of p dimensions each. So the first part is a set of p input gates. The second part is a set of p forget gates, which is denoted by f. The third part is a set of p output gates, and the fourth part is a set of p cell increments. So this is how this C is what you're going to use to change the value of your long-term memory. So only the first of the 3 are really gates. Now note that I've used sigmoids for the first 3. So these sigmoids, they're element-wise sigmoids applied to p-dimensional vectors. So your I, which is a set of input gates, is going to turn out to be a set of values between 0 and 1. Same about F and O, which are going to be values between 0 and 1. Now these are your gates. These are analog gates between 0 and 1. It's helpful to think of them as binary gates, which are exactly 0 and 1. Because that helps you understand how these updates, the way in which these updates are really controlled. And now, if you look at the right hand side of this update equation, especially the past part where we are multiplying the 2p dimensional vector with WK, it looks a lot like the recurrence equation of a multilayer recurrent network. So you can see it's WK multiplied, except that we are multiplying with a much larger weight matrix here, and we are using it to create 4 intermediate variable vectors. We are not straight away creating the hidden vector. So let's see how we use these intermediate variable vectors in order to update the hidden states and the cell states. Now it's very important to note that these intermediate vectors, you don't carry them forward from layer to layer. They're just intermediate variables which you use to update your 2 main variables, which are your hidden states HTK and your cell states CTK. You don't care, once you're done with the operation, you don't care about these 4 specific sets of variables which you have set up in this step. So first let's talk about the long-term memory. So you can see the long-term memory, it uses a bunch of element-wise operations. So you take the cell state in the previous timestamp, you multiply it with the forget gate. You do an element-wise multiply with the forget gate. So what it's telling you is that for each of these cell states, you have a vector of p-dimensional forget gates. So you have p forget gates and you have p cell states. You're telling, okay, which of them am I going to copy or not? Now, if you interpret them as binary gates, you are basically making a binary decision which of the cell states to copy to the next timestamp. But here you have analog gates. So the values of f, they are typically between 0 and 1. And you're copying a portion of them. But then there's also an increment portion to the to this update. So if you look at equation 3, the second part of it, that is the element by wise multiplication of the input vector with C. Now the C also was set up in the previous slide. If you look at equation 2, you have the cell increment right at the very bottom on the left of equation 2. You have the cell increment C. This was set up. And note that here a tan F function was applied. So this value, the cell increment can be anywhere between -1 and 1. And you're using this cell increment along with the input gates. So the input gates are deciding should I add something to the long-term memory or not. We have already made a decision using the forget gate whether or not you should copy and how much you should copy using the analog gates corresponding to F. The forget values. Here you are using the input gates to decide how much to add to your long-term memory. Now in this long-term memory, you are essentially, what you're doing is that you're copying a part of the memory, which is a very gentle operation. And at the same time, you're allowing a small amount of iterative increment. So you can think of this as iterative feature engineering. Now most of the time when we have discussed about operations in neural networks, we always talked about hierarchical feature engineering, which is essentially a matrix multiplication followed by a nonlinearity. That's hierarchy. Here it's iterative feature engineering, and this principle is very useful for deeper networks. And in fact, as we'll see in a later lecture, there is a convolutional neural network called ResNet, where you can get hundreds of layers by using this similar principle of iterative feature engineering. So this is the reason why long-term memory is so stable, because you're always copying from layer to layer. Another point that I would like to mention, these forget gates, they are initialized in such a way using biases so that the forget gates in initial iterations tend to have high values, that is values which are much closer to 1. Now in these sets of updates, I have not introduced the biases for the various variables. In reality, in neural networks, you almost always use biases associated with different variables. So the way in which you set the biases of the forget gates, in the initial iteration, most of the forget gates are very close to 1. So most of the values of the long-term memory are being copied from layer to layer. So especially in the initial set of iterations, the vanishing and exploding gradient will not happen because the values of F are very close to 1. And now that we have this stable set of cell states which are copied from layer to layer, you can selectively leak some of this long-term memory to the hidden state. So what you do is that you take this cell state, you apply the tan function to it, and then you again do an element-wise multiplication with the output gate. So now note that this output gate was also set up in the previous slide. If you look at the equation 2, the third element of the vector, it's a set of p-dimensional elements. Those are a set of output gates. So now because you are multiplying this stable cell state with the output gates in order to get your hidden vector, the gradient flows for the short-term memory are also stabilized. Now the other point is that in some variations you don't actually even use the tan F function. So you just use the raw cell state and you multiply it with the set of output gates. So in that case, the short-term memory is even closer to the cell states. So if the cell states are stable, generally the short-term memory will also be quite stable. And now, in order to understand why gradient flows in an LSTM tend to be far more stable as compared to a vanilla recurrent network, let us examine an LSTM with one dimension. Now, if you have an LSTM with one dimension, then this equation 3 over here, you can write it for a single dimension. So I've replicated this equation 3 in equation 5 for a single dimension. So here you just have a single dimension, single layer, the simplest case. So you have Ct is equal to Ct minus 1 star F, that's your forget gate, plus I star C. C is your new cell increment, which you set up in the previous layer. Now the partial derivative of Ct with respect to Ct minus 1 is F, which is simply a forget gate. So you are multiplying the gradient flow with F. Now note that even though F is less than 1, the way in which you initialize your forget gates, typically in the initial iteration, the value of your forget gate is very close to 1. So what's going to happen is that your gradient flows will be quite stable from layer to layer. Now, here you note that we are using element-wise multiplication. If you look at all the previous equations, you have this O dot, which is an element-wise multiplication. So this idea of equation 5 about how gradient flows are carried backward, it easily carries forward to the case when P is not 1, when you have p-dimensional states for any P greater than 1. Now, the other point is that in a vanilla recurrent neural network, one of the reasons why you have the vanishing and exploding gradient problems is that you have the shared weight. So in every iteration, when you look at what you're multiplying with, when you look at the transfer Jacobian, a component of that comes from the weight matrix. So because the portion of that multiplication is always the same, it tends to exacerbate the vanishing and exploding gradient problems. On the other hand, here, these f's, these forget gates, they are intermediate variables and they will vary from timestamp to timestamp, and this tends to make it less likely to cause vanishing gradients. So often the forget gates, their values are decided in a data driven way. So if a forget gate is less than 1 for a particular element of the cell state, that's because the data really suggests that it should be so. The other point is that the gradient flow for CT is inherited by HT, because you have HT is equal to the output gate multiplied by the tan A of CT. So when you take the derivative of HT, you simply have to take a single tan A derivative with respect to CT, and of course you have to multiply with the gradient flow for CT. So because you're just on a single tan A derivative, again the gradient flows are far more stable in the case of the short-term hidden memory. Now, these LSTMs, by and large, they have replaced vanilla recurrent neural networks. And most of the applications that we discussed in the previous lecture, we discussed them using a simple single-layer vanilla recurrent network. In reality, in most real applications, you would be using a multi-layer LSTM. You wouldn't be using a vanilla recurrent neural network. Now, in the case of the LSTM, we have a separate short-term memory and a separate long-term memory, with the long-term memory playing the primary role of stabilizing gradient flows. It turns out that it's actually possible to have stable gradient flows without having a separate long-term memory, and that is the idea of the gated recurrent unit. So you retain the idea of gates in order to control gradient flows and copy portions of the state from layer to layer, but you don't really need a separate long-term memory. Of course, the main idea here is that as long as you copy a part of the state from layer to layer in a careful way, the gradient flows are largely stabilized. So let's look at the gated recurrent unit, which performs these types of careful updates in order to have stable gradient flows. The gated recurrent unit is essentially a simplification of the LSTM, where you use fewer gates, and because you use fewer gates and you also use fewer number of cell states, there are fewer number of variables you need to use. So in this case, we are using two matrices, WK and VK. Now this WK, again, this matrix is used to set up the gates, but instead of using a 4P cross 2P matrix, you are using a 2P cross 2P matrix, because you will have fewer gates in the case of the gated recurrent unit. And also you have VK, which is a matrix of size P cross 2P. So, of course, the first layer, again, you treat it specially, as we discussed for any multilayer network. When k is equal to 1, the matrix of size 2p cross p plus d and p cross p plus d. That is because the hidden state at k is equal to 0 is simply the input vector, which is a d-dimensional vector rather than a p-dimensional vector. Now, in the case of the GRU, you have two intermediate p-dimensional vector variables, which are ZT and RT. ZT is referred to as a set of update gates, again a p-dimensional set of update gates, and RT is a set of reset gates. So now you can see that we are setting up equation 6 in a very similar manner to the way we set up the LSTM. So if you, for example, look at equation 6, if you look at WK, HTK minus 1, HT minus 1K, it is very similar to equation 2 over here. So if you look at equation 2, again you have WK, except that WK here is a 4P cross 2P matrix. In this case, your WK is a 2P cross 2P matrix. So you get a 2P dimensional vector, and for each of the, so you can divide into 2 blocks of P dimensions each. And for each of these blocks, you're applying the element-wise sigmoid to get again 2 blocks. One block is the set of update gates, a P-dimensional set of update gates, and another block is a P-dimensional set of reset gates. And now you use the update gates to control how much you copy the hidden state from layer to layer. Now note that in the case of the LSTM, the gradient is stabilized by using the notion of copying from layer to layer. So your update gate, this Z, the P-dimensional vector corresponding to Z, plays that role. But it also plays the role of deciding how much to increment. It also plays the role of what was played by the input gate in the case of the LSTM. So here you can see you are multiplying, doing an element-wise multiplication of the Z vector with the hidden state in the previous time frame, which tells you how much of the hidden state to copy from layer to layer, and then you're using 1 minus Z multiplied by, now this is a matrix multiplication based update. Now this matrix multiplication based update also is slightly modified because as you can see you're using a reset gate for the previous timestamp. So the reason you're using a reset gate from the previous, if you look at equation 7, the rightmost expression, the lower right, if you look at the vector, the lower expression of the vector on the right of equation 7, that's R element-wise multiplication with the hidden state at the t-1 timestamp. The reason in which you reduce the effect of the t-1 timestamp here is because a part of the timestamp we are copying. We are already copying it using the update gate. So if you look at the first portion that's being copied, but you're reducing the effect on the matrix-based portion. So by reducing the effect on the matrix-based portion and increasing the weight of the copying portion, you're tending to stabilize the gradient flows. So let's explain these updates. So the reset gate decides how much of the hidden state to carry over from the previous answer for a matrix-based transformation. So the matrix-based transformation is a strong transformation. And I'm saying how much of the hidden state from the previous timestamp should I apply a strong transformation on that, on it. And then the update gate decides the relative strength of the matrix-based update and a more directly copy from the previous timestamp. And the direct copy on the previous timestamp, actually it stabilizes the gradient flows. So in order to understand how it stabilizes the gradient flows, let's look at a one-dimensional single layer GRU update. Now note that we also had discussed a one-dimensional single layer LSTM update. Here we are going to discuss the same for a GRU. So in this case, the hidden timestamp at HT is given by Z multiplied by HT minus 1 plus 1 minus Z given by this expression over here. Now this V1 and V2, these are two elements of your small matrix V. Now this matrix Vk, now note that here K is only 1. So we have a single layer matrix, so I don't need a superscript here. So we don't have any superscripts in this expression because I'm using a single layer, one dimensional single layer GRU. So, but your matrix Vk, because you're looking at the one-dimensional case, your matrix Vk will be 1 cross 2 matrix. So it will have two elements, your matrix V, which is V1 and V2. So these V1 and V2, these are two elements of the 1 cross 2 matrix. So here equation 8 gives you the update for the GRU when you use a one-dimensional and single layer GRU update. Now you can compute the derivative. You can compute the derivative of HT with respect to HT minus 1. You are going to get Z plus a bunch of additive terms. So this Z really comes from the copying from layer to layer, and it helps in passing unimpeded gradient flow, and it makes the computation more stable. The other point is that when you look at the additive terms, they heavily depend on 1 minus Z. So if Z is small, the additive terms will tend to compensate more and will tend to make this gradient flow closer to 1. The other point is that again we are setting up these update variables corresponding to Z and R, which may be different for each timestamp. So in each timestamp you will be multiplying by a different amount, which tends to make the gradient flows a bit more stable. Now, this kind of stability, it is ensured by the notion of partial gating. And when you're using partial gating to copy the portions of the stage from timestamp to timestamp, they often refer to this principle as what you call highway networks. Now, there are many variations of the LSTM and the GRU. A very extensive comparison of many different variants of the LSTM has been performed in this paper, LSTM, a Search Space Odyssey. And what they showed is that for different applications, some variants of LSTM tend to perform better, but none of them could reliably outperform the vanilla LSTM. This is quite remarkable because the LSTM was set up in the late 90s, and in spite of that fact, none of the variants have really been able to do much better than than the simple LSTM. The other point is that when the LSTM was set up in the 90s, generally it didn't work well. The reason is that at that time we didn't have a lot of data. But in recent years we have more data, and of course our training methodologies have become much better. We have a lot of many different gradient descent methods, second order gradient descent methods, normalization methods, which have tended to make the training of these methods much better. So along with increased data, computational power, and better training tricks, almost these same models, they have become very useful in recent years. Now the LSTM has also been compared to the GRU. There are some empirical comparisons in these two papers that I have listed here. And in both of these cases, there isn't a clear winner between the LSTM and the GRU. In general, because the LSTM contains a larger number of variables than the GRU, it would make sense to use the GRU in cases where the amount of your data is limited, or you want a quick implementation, because the GRU is a much simpler model to implement. On the other hand, if you have a lot of data and you want something that you can predict a little bit more, perhaps the LSTM might make more sense. So in general, even after all these years, the LSTM remains as the method of choice among all the different variants that have been proposed for recurrent networks.